The dogma I worry about is that we should think about physics in terms of time evolution, this picture where you start at the beginning and evolve forwards in time. That's a very intuitive way of thinking about physics, but it is very clearly not a good fit for what we are seeing. There's really good evidence coming from lots of different parts of physics that we shouldn't be thinking about time in those terms.
Imagine a completed Sudoku puzzle. The rules don't dictate that you start in one corner and then work systematically across the grid. Instead, they just constrain what patterns are valid for the entire puzzle. Professor Emily Adlam of Chapman University suggests that the fundamental laws of physics work similarly. You don't evolve the universe step by step from past to future. Instead, there are these constraints, something that selects valid patterns across all of space-time simultaneously. This quote-unquote all-at-once perspective helps explain paradoxical quantum phenomena like delayed choice experiments and Bell non-locality. It also comports with Einstein's relativity, where the distinction between past and future depends on the observer's reference frame. If correct, this paradigm shift would transform our understanding of causality, of observers, and of the nature of physical law itself. What's the largest unsolved problem in physics today that you're interested in?
Well, this is not a very original answer, but I think the measurement problem of quantum mechanics for me still really stands out as an important unsolved problem. And not just because it's sort of intellectually interesting, but because it seems to me that it's closely linked to a variety of concrete problems that we're working on in modern physics. So in particular, I think in the context of work on quantum gravity, a lot of the issues we're really sort of struggling with are ultimately to do with the nature of observers, the nature of observation. So for example, solving the problem of time is all about trying to understand how to put the observers into their theories in the way that reproduces the kinds of observations we expect to see. And so that makes me think that perhaps there's an issue here where we never really came to grips with how to think about observers in the context of ordinary quantum mechanics, and that's really holding us back from making us progress on further physics. So I think that problem, to me, demands a solution not just for intellectual curiosity, but also to be able to make real progress.
And what's the definition of observer? Is it the same as a measuring device, or what counts as a measurement?
Well, that's exactly the problem. We don't know clearly how to define observers in concrete physical terms. We have, of course, an intuitive notion of what an observer is, and we know what we expect observers to see, but it's still very unclear how to properly model observers within quantum mechanics. All the interpretations of quantum mechanics say something different about how you should represent observers, and that has important knock-on effects for how you're going to think about observers in the context of further physics like quantum gravity.
How does the problem of observers, or defining what observers are, have anything to do with quantum gravity?
So, one of the big problems we encounter in the formulation of quantum gravity is known as the problem of time, which refers to the fact that if you impose a sort of canonical quantization on gravity, the result is that time evolution seems to vanish. You end up with this sort of strange timeless model. And so then one obvious problem you have is try to understand how the kinds of experiences that we have could possibly arise in this context. Where does our sense of doing things in time and obtaining outcomes come from? And so there are lots of interesting ideas around this, but a lot of this is still very focused on this question of how exactly should you represent an observer? How can you make sense of sort of local observations in this setting?
So why don't you tell us how you make sense of observers then?
Unfortunately, I don't have a complete answer to this question. I think one thing that we can see clearly from both general relativity and quantum gravity is that making sense of observers is probably going to require understanding them in sort of relational terms, understanding observations as things that happen in some sense relative to observers rather than being things that are out there in the world by themselves. So that seems like an important insight, which I think is also relevant for standard quantum mechanics, but certainly it's an ongoing project to understand exactly how to make that work in a coherent way.
We're going to get to the relational interpretation of quantum mechanics and your work with Carlo Rovelli. But prior to that, I want to know, what the heck is a Sudoku universe?
Yes. So the Sudoku universe is a way of thinking about time and laws in the context of modern physics. So there's this perhaps quite traditional way of thinking about physics where we imagine it as something like a computer, as Ken Wharton puts it. So we think of an initial state being put in, and then the universe just evolves the initial state forwards in time and produces the course of history. And that's, I think, the intuitively natural way to think about physics that many people still use. But there's, I think, really good evidence coming from lots of different parts of physics that we shouldn't be thinking about time in those terms. We should instead be thinking about the laws of nature as applying all at once to the whole of history. So in that sense, they're like the rules of a game of Sudoku. The rules of Sudoku don't tell you to start at the left and then move towards the right. What they do is constrain the whole grid and tell you whether an entire solution is valid or invalid. So the thought is that the laws of nature perhaps work like that and not like time evolution.
Is that the same as saying that there's some imposition of consistency?
So certainly consistency is one important kind of constraint. I think probably we need more constraints than just consistency, because I don't know how to derive the actual laws that we observe from purely consistency conditions. It would be neat if that could be done, but it seems like there might be some constraints going beyond just consistency conditions to sort of impose the specific types of laws that we actually see.
You had a 2018 paper called Spooky Action at a Temporal Distance, which is a great title, by the way. You mentioned something becoming a dogma in physics. I'm quoting you, a dogma, and something like there's an assumption which is actively limiting progress in quantum foundations. So what is it? And those are strong words. So I'd like you to justify your usage of that language.
Yes. The dogma I was worrying about there was this idea that we should think about physics in terms of time evolution, this picture where you start at the beginning and evolve forwards in time. As I say, that's a very intuitive way of thinking about physics, but it is, I think, very clearly not a good fit for what we are seeing in modern physics. And yet, nonetheless, many people, I think, are still drawn to try to think about things in those terms. So, for example, in quantum foundations, it's very common to be quite focused on trying to give causal accounts of things to understand either in classical terms or to move to a sort of quantum notion of causation where you can tell the story about one thing causing another thing causing another thing. And that, I think, is not a good use of our effort, because there are clear indications that that's not really the structure that physics actually has. And so trying to force it into a causal structure is not likely to be a good way of understanding it.
In the philosophical literature, there's dispute as to what is causation. Do you have a personal account of causation?
Yeah.
When I say personal, I mean one that you favor.
Yes. So definitely the accounts of causation I favor are the ones which suggest that causation needs to be understood as essentially as a macroscopic phenomenon. So causation, I think, clearly has something to do with thermodynamics and the thermodynamic arrow in terms of entropy. It's also, I think, clearly related to perspective, the perspective of macroscopic observers like us and what we can and can't achieve. It's related to interventions and telling a story about what observers like us can achieve by intervening on certain types of variables. So all of those things make it seem very macroscopic in nature, which means that for me, it's incorrect to think of causation as being something that inheres in the microscopic world. Certainly there are, I think, important kinds of structure in the microscopic world that we need to think about, but I don't think those structures are causal in the ordinary sense, and so it's not going to be particularly helpful to try to model them in causal terms.
So I'd like to talk about non-locality as well, specifically temporal non-locality.
Yeah.
And in temporal is time. And earlier you mentioned the problem of time. And then here we're talking about the arrow of time or the thermodynamic arrow of time. So it sounds to people who know some physics that, oh, there's a problem of time. Is that the problem of the arrow of time? Is the problem of time different than the arrow of time problem? And does the second law solve it? All of these get entwined in their mind. So why don't you distinguish those? What is the problem of time? What is the arrow of time and what it has to do with the second law?
Yes. So the arrow of time usually refers to the fact that in the world as we experience it, there are all these temporal asymmetries. glasses break and don't usually recompose themselves, all of these kinds of obvious asymmetries that characterize our lives. And the problem of the arrow of time is that the underlying physics mostly seems to be time symmetric. So in that sense, it's not obvious where all of these asymmetries could come from. You seem to have to impose them by just deciding by fiat that the initial state of the universe is some special kind of state which can explain those asymmetries. But for many people, that's not super satisfying. The problem of time in quantum gravity is a distinct issue. It refers to the fact that within a specific technical formalism for quantizing gravity, when you perform that quantization, you find that time evolution ends up being what's called a gauge transformation, which means that it's not physically real. It's just kind of giving two different descriptions of the same thing. So it looks like time evolution in the ordinary sense is not present at all. So that leads to a problem of trying to understand, where do our experiences come from? Why do we have these experiences that feel like they are temporal in nature? So they are separate problems, but I think it's very likely they are linked. I think certainly the story about why we have experiences which are temporal in nature must have something to do with thermodynamics and the fact that we live in this very asymmetric regime. So there's still work to be done to flesh out the connections between these things, but certainly I think they're not completely independent.
So some people explain the arrow of time with coarse graining. I think Stephen Wolfram does this.
Yep.
And in coarse graining is the notion of renormalization. You had a paper on why reductionism is false, or at least not necessarily true, and you tied it to renormalization.
Yep.
Can you please talk about that?
Yes. So in that paper, this is sort of an exploratory paper. I'm not necessarily committed to the view that that reductionism is false, but I'm interested in whether that is maybe one way to try to resolve some of the problems that we encounter in quantum field theory. So one of the problems is a sort of fine-tuning issue where we find that in certain kinds of cases, it seems that the values of two distinct fundamental constants must be very carefully adjusted to fit each other in order to produce the observed value of the constant at a higher scale. And sort of the observation I was making here was that if you say things are the other way round, if you say that the higher level constant is fundamental and the smaller scale constants are in fact derived from it, that gives you a very natural explanation for why they're fine-tuned in this way, because they are in fact fixed by the actual value of the higher level constant. So the thought there was just that perhaps changing our way of thinking such that in some cases smaller scale things are explained by larger scale things rather than vice versa might be a way of understanding some of those phenomena. So then it was important to look at the renormalization transformations, because renormalization is the transformation we use in quantum field theory to move between different scales. And so the question I was looking at there was trying to understand, given the mathematical structure of the renormalization translations, is it possible that things could be reversed in direction and that the higher scale things could define the lower scale things and not vice versa?
Mm-hmm.
We normally wouldn't think that's possible in sort of more ordinary physics, because we think there's a sort of many-to-one mapping where many microscopic possibilities get mapped to one macroscopic possibility, so the macroscopic possibility can't determine what's going on in the microscopic scales. But renormalization is in fact a one-to-one transformation. So it does seem more plausible in the kind of regime where that's relevant, that perhaps the higher scale things could determine the lower scale things because of the specific mathematical structure of that transformation.
Even at fixed points?
So fixed points are somewhat more complicated because fixed points do involve scenarios where many solutions get mapped to one solution. But the thing about fixed points is that they can occur both at very small scales and at larger scales. So it's not obvious to me that invoking fixed points particularly favors one direction of explanation, since they occur at both levels.
So let me see if I can phrase this in the language for mathematicians, and correct me if I'm incorrect. The renormalization group is a set of tools to determine how parameters change with different scales, whether it's energy scales or length scales or what have you. Now, it's less of a group in the algebraic sense and more a set of tools, but if it was to be something like a group, it would be a monoid, because not every element is invertible. However, most of the elements are invertible, and this would mean that you don't privilege some scale as being more fundamental in the same way that in an affine group you don't have a privileged origin.
That's right, yeah. So we have various approximations we use to do renormalization, and many of those are not invertible. But there are good reasons to think that the real underlying transformations should be invertible. And if that's the case, then outside of fixed points, you can go from small scales to large scales, or you can go from large scales to small scales. It's kind of the same from the point of view of the underlying math. And so there's no sort of obvious sense in which the physics is telling you the small things must explain the big things and not vice versa.
Hmm. Let me see if I can make another analogy. So let's imagine there's a bird in the sky and you take a snapshot
Yeah.
of that bird.
hmm
And then you say, okay, its position is here and its velocity is here. So, or its momentum. And then you could say, okay, where is it going to be? And then you can plan out its, or you can predict its trajectory. And then you say, well, look what we got here as an initial position and velocity. But why did you call this initial? Like you could actually, from another point, make the trajectory go backward, and so you have the whole trajectory. So what is the initial point? Why is one point being privileged?
Yeah, I mean, I think that's a great analogy, because I would say much the same about time evolution as well, that there is no particular reason to privilege one point. Certainly, the physics doesn't tell you have to do that. And yeah, I think the same is true, at least for many applications of the renormalization transformation. The physics doesn't seem to be telling you that the smallest, most fundamental scales must actually be privileged in that sense.
So let's get to non-locality. There's a large hubbub about non-locality and Bell's theorem and also realism.
Yeah.
Well, what is non-locality?
Yeah, so in the context of quantum mechanics, non-locality is the phenomenon that quantum mechanics exhibits correlations which seem to be too strong to be explained by any local model. So normally when we see correlations at a distance, we would expect to explain them by some common cause in the past. They both came from the same source or something like that. But Bell's theorem demonstrates that the types of correlations we see in quantum mechanics can't be explained that way. It seems as though there's some kind of direct influence between events happening at a distance that can't be explained in this sort of common cause way.
Now, there's two different types of non-locality, spatial and temporal. And you have many papers, many talks as well on temporal non-locality. So please distinguish the two.
Yeah, so perhaps the traditional way of thinking about non-locality in quantum mechanics is to imagine it as a spatial form of non-locality. So that involves a situation in which perhaps Alice performs a measurement in one location, and as soon as she does that, the wave function collapses everywhere in the world, and that sort of conveys information across to Bob wherever he is, and that has an impact on the result of his subsequent measurement. So that non-locality is spatial because the effect of what Alice does is just transferred to the whole global state everywhere at the same time. Whereas temporal non-locality suggests that non-locality doesn't necessarily have to be conveyed immediately in terms of the current state of the world. You can potentially think of non-locality as kind of hopping across time as well. So Alice performs her measurement at some time, and at some other place and at some later time, Bob performs a measurement, and there's just a direct relationship. There's some kind of constraint requiring that Bob's outcome reflects Alice's choice in some way. So there's a kind of direct non-local impact that is not mediated by a global state evolving forward carrying that information.
Does spatial non-locality imply temporal or vice versa?
Yes, so I think combining spatial non-locality with relativistic constraints makes it very compelling to think that there should be temporal non-locality. That's because if you take a frame of reference within a relativistic setting where you have a spatially non-local effect, something Alice does influences something that happens over here, you're allowed within relativity to make a change of reference frame to get another equally valid reference frame. And in that reference frame, those events are not going to be at the same time anymore. The event, Bob's event over here, is going to be either in the future or the past of Alice's observation. So it looks like by making that transformation, you have turned your spatial non-locality into temporal non-locality. So that, in that sense, if you believe what relativity tells us about the close connections between space and time, it seems very hard to maintain that non-locality is always spatial and never temporal.
Mm-hmm. So then why is it that physicists, if I understood one of your papers correctly, why is it that physicists focus on the spatial non-locality when if you're in the relativistic setting and both are on quote-unquote equal footing, a term I don't like for various reasons. I'll put a link to a video on why I don't like equal footing, but regardless, why is it that physicists tend to focus on the spatial non-locality compared to the temporal one?
Yeah, well, I think one main reason for this is because quantum mechanics historically and still usually today is formulated as a time evolution theory. So the natural way to think about quantum mechanics in its standard formulation is to sort of formulate it in terms of global states which carry all the information forwards in time. So from that point of view, if you're trying to model locality in that picture, perhaps the sort of natural thing to do is have a global collapse of the wave function that takes place everywhere, and so to have spatial non-locality. If you are formulating quantum mechanics in a different way, as a non-time evolution theory, then temporal non-locality becomes much more sort of natural and compelling, but that's not the traditional way in which we have formulated quantum mechanics.
Is the future influencing the past an example of temporal non-locality?
Yes, so it could be. It depends how you think about the way in which the future influences the past. If, for example, your model of the future influencing the past involves some kind of like backwards evolving state that goes back and carries the information backwards in time, you might end up with a picture where there is a backwards influence, but it is sort of locally mediated by a backwards evolving state. On the other hand, if your model of the way in which the future influences the past is some kind of all-at-once style model where there's just a sort of global constraint relating these two things to each other, in that case, it is going to look much more like temporal non-locality because there doesn't need to be a sort of literal state that goes back and carries the information.
Right. In your work, as I was going through it, you differentiate between dynamical retrocausality, so influences propagating backward in time step by step,
Yeah.
and then this all at once. And this term all at once will come up over and over. And I believe it's an all at once temporal retrocausality.
Yes.
But would it be called retrocausality at that time? At that point, if it's all, I guess that's a pun. Would it be called retrocausality if it's happening all at once?
Yeah.
Why is it retrocausality?
Yeah. I mean, well, I use retrocausality in this connection just to sort of, in a loose way, to relate what's going on here to sort of more traditional discussions of retrocausality. I think, strictly speaking, what's going on there is not retrocausality because I think there's no causality in fundamental physics. So, neither the forwards nor the backwards direction is truly causal. But certainly, if you try to look at this from a more macroscopic point of view, and you sort of write down a causal model in which a person intervenes on something, in that sense, you're going to get effects that look retrocausal from that macroscopic point of view. Even though I do think that you should acknowledge that at the fundamental level, none of this is causal.
So when you're thinking about all at once, are you also thinking about boundary conditions? So the ordinary way that physics is thought about is that you have your boundary conditions plus the laws, and you then evolve forward. So please define what all at once is.
Yes. So, I mean, all at once refers to this sort of Sudoku universe style idea where the laws of nature apply to the whole of history all at once. So the one possible type of all at once model is a model in which you fix the initial and the final conditions, and then you ask the laws to determine what happens in between. And that's quite a common type of problem that we see even in fairly standard physics. But it's also not the only kind of possibility. When I talk about all at once or constraint-based laws, I usually talk about the laws of nature fixing, determining the whole history at once. So in that sense, often it will be the case that you can fix any state anywhere on the history, and that will be sufficient to fix the rest. So it could be the initial state, could be the final state, could be one or more states in between. In that sense, in that kind of picture, no particular point of time has to be specially privileged. It's just the history as a whole which is selected by the laws.
When speaking about these histories, it reminds me of the transaction interpretation. Have you done any work on the transaction interpretation, or do you have any thoughts on it?
I think the transactional interpretation is certainly interesting. I'm interested in these kinds of retrocausal models. Um, uh, I guess I would like to see more emphasis from the transactional interpretation on moving away from specific experimental situations to a more general picture where I can understand how the experimental situations and the observers in particular are supposed to arise from something more fundamental than that. In some cases, the transactional interpretation seems to me overly focused on a setup where we already have, where the instruments and the observers are kind of already given.
Tim Maudlin had a challenge to the transactional interpretation about how there's some contradiction in simple backward causal stories.
Yeah.
Does the all at once... Okay, so firstly, what is Tim Maudlin's objection or challenge? And what does the all at once model do to resolve it?
Yeah, so I mean, Maudlin's concern was that if you imagine an experiment in which we take some sort of preliminary measurement in the middle of the experiment, and then we use that to determine part of the final conditions, the final measurement we're going to make. That looks inconsistent with the most naive version of the transactional interpretation, because the transactional interpretation is supposed to take the initial and final conditions and determine what happens in between. So you can make that become contradictory. So there are more sophisticated versions of the transactional interpretation which avoid this issue. But I think all of them ultimately avoid this issue by moving away from the sort of naive story where there's a literal transaction taking place in some sort of temporal process, and more towards an all-at-once style picture where the whole thing is kind of atemporal and has to be thought of as being determined in this atemporal sense that fixes its consistency. So I think ultimately resolving that kind of problem, both in the transactional interpretation and in retrocausal models more generally, does seem like it's going to push you towards an all-at-once style picture.
We started this conversation with talking about the largest problem that irks you, and it was the measurement problem. And now we're talking about the all-at-once model. Did the measurement problem lead you to this all-at-once quantum framework, or did you starting this all-at-once quantum framework lead you to realize the importance of the measurement problem?
I think they are separate in that, I think the indications that the all-at-once model is correct come partly from quantum mechanics, but also from other parts of physics, from relativity and quantum gravity and so on. And I think just adopting an all-at-once style model does not by itself solve the measurement problem, because the measurement problem is to a large extent about how to model observers. Just saying we're going to tell an all-at-once story doesn't answer the question of how to model observers. So I do think that it seems clear to me that the right solution to the measurement problem is going to be some all-at-once style solution, but there are a number of different possibilities within that. And so I think it's still, for me, open which is the right way to do that.
Do you find cubism or other observer-centric interpretations to be unsatisfactory?
I find them incoherent. My worry about them is that if you're really serious about your observer centricity, that is going to lead you inevitably to a picture in which every observer kind of has their own little reality and they're not able to communicate with each other. That, I think, is incompatible with the practice of science. Science is a very social activity. The sort of objectivity of science rests on the fact that we have all these different scientists doing observations and then sharing them. So I don't think it's reasonable to interpret quantum mechanics in any way which ultimately says we can't actually communicate with different observers. I am, however, interested in sort of more moderate observer-centric views which allow that observers play an important role, or that perspectives in general play an important role, but which nonetheless make provision for sort of connections between perspectives to happen.
Such as relational quantum?
Yeah, so I mean, relational quantum mechanics in its standard formulation does have the problem that I've just described, because it does imply that it is impossible in a sort of absolute sense to ever know anything about what's going on in anyone else's perspective. But the work that I did with Carlo Rovelli recently was about thinking about how could you alter relational quantum mechanics to overcome this issue. And so we did suggest a possible way to address that by adding a postulate which allows communication between observers.
Just a moment. Don't go anywhere. Hey, I see you inching away. Don't be like The Economy. Instead, read The Economist. I thought all The Economist was something that CEOs read to stay up to date on world trends. And that's true, but that's not only true. What I found more than useful for myself personally is their coverage of math, physics, philosophy, and AI, especially how something is perceived by other countries and how it may impact markets. For instance, The Economist had an interview with some of the people behind DeepSeek the week DeepSeek was launched. No one else had that. Another example is The Economist has this fantastic article on the recent dark energy data, which surpasses even Scientific American's coverage, in my opinion. They also have the chart of everything. It's like the chart version of this channel. It's something which is a pleasure to scroll through and learn from. Links to all of these will be in the description, of course. Now, The Economist's commitment to rigorous journalism means that you get a clear picture of the world's most significant developments. I am personally interested in the more scientific ones, like this one on extending life via mitochondrial transplants, which creates actually a new field of medicine, something that would make Michael Levin proud. The Economist also covers culture, finance and economics, business, international affairs, Britain, Europe, the Middle East, Africa, China, Asia, the Americas, and of course, the USA. Whether it's the latest in scientific innovation or the shifting landscape of global politics, The Economist provides comprehensive coverage, and it goes far beyond just headlines. Look, if you're passionate about expanding your knowledge and gaining a new understanding, a deeper one, of the forces that shape our world, then I highly recommend subscribing to The Economist. I subscribe to them, and it's an investment into your intellectual growth. It's one that you won't regret. As a listener of this podcast, you'll get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/toe, TOE, to get started. Thanks for tuning in, and now let's get back to the exploration of the mysteries of our universe. Again, that's economist.com/toe. How is it that you think about probabilities? Like, there are different interpretations of probability. Forget about quantum mechanics. There are different interpretations of what a probability is.
Yes.
So in metaphysics and in science, how do you think about probability?
Yeah, I think the interpretation of probability is a very hard problem. I think I'm not wholly satisfied with any of the approaches that we have available to us. The sort of frequentist approaches are useful in many cases, but have pretty significant philosophical problems for us accounting for certain kinds of edge cases. Subjective Bayesianism, I think, just doesn't do justice to the fact that certain probabilities do seem to be out there in the world and not just in our minds. The sort of dispositionalist accounts are quite mysterious and also very hard to reconcile with all-at-once style physics. There are a couple of recent approaches that I'm very interested in. There's a view called gnomic frequentism, due to someone called John Roberts, which suggests that probabilities should be understood as in terms of laws which require that frequencies should look a certain way. And there's some really nice work on this recently by Eddie Chen and John Barrett, looking at the ways in which you could potentially expand on that and think about probabilities as sort of constraints on relative frequencies. So while that work is still ongoing, I think that's a really interesting direction and probably the most promising approach from my point of view.
What do you mean? What is Eddie Chen saying that probability should look a certain way? What does that mean?
So this is working within the sort of all-at-once style constraint-based view of laws. And the observation is that if you allow that laws are global constraints which apply to the whole of history, then you can formulate a probabilistic law as saying something like the relative frequency of occurrences of some outcome across all instances of this type of measurement across all of history must have some value or must fall in some range. So you can think of the laws or probabilities as directly constraining the relative frequencies that actually occur. So that's somewhat similar in spirit to the frequentist approaches, but I think avoids some of the more serious problems for frequentism, because it's not just saying that probabilities are whatever the frequencies should happen to be. It really is saying that the laws constrain the frequencies and require them to have certain values.
So how does your approach compare with Shelley Goldstein's approach?
Yes. So the approach that Eddie Chen and Shelley Goldstein have worked on in terms of laws is, I think, very similar in spirit to mine. Indeed, Eddie and I are working on a project sort of examining some of those similarities. Mm-hmm. But perhaps one difference is that one difference is that they are inclined to think of those all-at-once constraints as a sort of fundamental primitive, whereas I perhaps prefer to think of them as being a form of modal structure in accordance with a sort of generally structurally realist approach to physics and to laws. But I don't think those views are necessarily incompatible with each other. They're more sort of a difference in emphasis.
What's a modal structure? What does that mean?
So modal is a word that philosophers use to refer to facts about what is possible and impossible.
Mm-hmm.
So modal structure, perhaps the most well-known example of modal structure is causal structure. So that's one form that modal structure can take. Because I don't think causation is fundamental, I don't think that can be the most general type of modal structure. But I do think the world has some other kind of structure, which is in some ways similar to causal structure, but perhaps more general than that. And so that's where I would sort of expect those all-at-once constraints to live.
Modal structures. So modal comes from philosophy. It's not a term you hear in theoretical physics. Now, it is when you start to study the foundations of physics or the foundations of quantum mechanics.
Yeah.
But I'm curious how philosophical tools, such as modalism or analyzing determinism or realism, has guided your research.
Yes, but I think there's a sort of useful back and forth to be had here. I think that modern theoretical physics has important lessons for a variety of traditional philosophical discussions. This discussion about lawhood is a great example. Both me and Eddie and Shelley are inspired by noting that traditional philosophical accounts of lawhood don't seem to do a very good job of accommodating the kinds of laws we see in modern physics. And I think there's useful sort of flow of information backwards as well, because using these philosophical tools and doing the work to analyze, okay, so what are laws now? How can we understand the types of laws we're seeing in modern physics? That's a useful way of clarifying our thought about what's going on in theoretical physics, understanding what are useful directions for future research, and sort of understanding how we can connect those developments back up to the kinds of things we're concerned with in philosophy and in everyday life.
Do you encounter the attitude from physicists that, hey, physics, experimental physics, theoretical physics, it doesn't need anything from philosophy? Philosophy hasn't contributed anything to science in the past 100 years other than maybe Popper, and before that it was a while, and you can't just count Aristotle, that was thousands of years ago. So do you encounter that attitude?
I think there's a wide spectrum of attitudes within physics. I mean, I certainly have encountered people with that attitude, but I've also encountered many physicists who love philosophy and are very interested in it and are very keen to talk to philosophers. So while that attitude does exist, I think there's also plenty of goodwill and interest in both communities to talk to each other and make progress.
What would be the counterpoint to someone who's saying that philosophy hasn't contributed directly to physics in the past few decades?
Definitely the most obvious example, I would say, is Bell's theorem and the discussion around non-locality. Bell's theorem was very much regarded as not mainstream physics when it was formulated. And Bell was a physicist, but other people involved in the discussion of non-locality and pushing this forward, like Shimoni, were not physicists. They were primarily philosophers. And certainly, I think this topic probably got more of a foothold within philosophy before it moved back into mainstream physics. But now it's certainly recognized as mainstream physics. The Nobel Prize was awarded for it recently. So I think that's an example of a case where topics that were considered sort of foundational and conceptual were worked on within philosophy for a while, but ultimately became recognized as part of mainstream physics.
Hmm. So what got you interested in philosophy? Did you start in physics or did you start in philosophy?
My undergrad was in both physics and philosophy, so I guess
Right.
both. I've always been very interested in physics and in science, but my questions have always been more on the side of what is considered to be foundational physics or philosophy of physics. I think it was a toss-up for a long time whether I was going to be a physicist working on the foundations of physics or a philosopher. My PhD is actually in physics, not philosophy. But, in the end, I think perhaps the kind of work I want to do feels like it lives more happily within philosophy. So that's why I ended up here.
And what does foundations mean? So when someone says they study the foundations of something.
Yes. So, I mean, generally that means something to do with they're interested in the sort of more basic conceptual questions, in looking at the sort of underlying structures, in perhaps understanding why the theory is the way it is, or understanding sort of basic principles of the theory. Sort of a contrast to, more applied approaches. So, if you study the foundations of quantum mechanics, you're not going to be primarily working on how to build new quantum technologies. You're going to be thinking about the structure of the theory and what it all means. And perhaps those results will eventually go on to be useful in quantum technologies. They often do. But if you're working in foundations, that's not your sort of primary focus.
So what I enjoy about your work is that, much like Jacob Barndis, you emphasize clarity of concepts and principles as a guide to progress. You actually co-authored a paper last year, if I'm not mistaken, with Sabine Hossenfelder and Tim Palmer, both of whom have been on the podcast before, so I'll put a link to that on screen and in the description. The paper is called something like A Taxonomy of Physics for Quantum Theory, or Beyond Quantum Theory.
Yeah.
It's something that everyone should read if they're interested in physics. And if you follow this podcast, you can follow that paper. So there are different concepts that are explained there with precision. I've heard local beables, be described as ontological entities. And I believe you said it's something like the input value on a C model that's assigned to a compact region of space-time. And you explained what a C model is. I think it's a calculation model, if I'm not mistaken. So anyhow, what led you to write that paper?
Yeah, this paper arose out of a conference on retrocausality and superdeterminism. Retrocausality and superdeterminism are two approaches that people have often tried to use in order to avoid the conclusion that quantum mechanics might be non-local. So this conference was kind of discussing those possibilities and can you get rid of non-locality using one of these methods. And I think what we discovered is that there were a variety of different ways in which people were using the words retrocausality and superdeterminism, and there was a sort of a problem where people were talking past each other because they were just using these words in different ways. So the goal of this paper was to sort of provide a clarifying story which would help explain what's going on with these terms, and perhaps can we have a sort of community-wide consensus about how to use these words so we can have discussions more clearly.
When people hear temporal non-locality, how is that different than time travel?
Yes. So time travel, much like retrocausality, could be temporally local or temporally non-local. If your vision of time travel involves people literally moving backwards in time, sorry, the cat is getting it. Involves people literally traveling backwards in time, that's going to look like a temporally local form of time travel if there's a sort of literal path back in time that they go around. On the other hand, if they just kind of disappear at one point and then reappear at another point, that's going to look temporally non-local because there's a sort of cause that just jumped across time. So I think either of those is possible as a model of time travel.
Does any of this have to do with free will?
Certainly, if you look at the all at once style of model, that does seem like it has some implications for free will, because some people have thought that something that's important to free will is the idea that the future is genuinely open, that in this moment as I am acting, there is no fact of the matter about what my action is going to be. And it's in an all-at-once style model, that way of thinking about free will is not available to you. The whole of the universe exists at once. I'm acting now, but there is already some fact from the atemporal point of view about what my action is going to be. So, I don't think that means we have to say there is no such thing as free will in that context. But certainly, we're going to have to be a bit more careful about how we analyze free will and what that means.
So this doesn't depend on determinism. It's just saying that there's something that's globally fixed.
Yeah, so even if you have a probabilistic model in the all-at-once context, what that's going to look like is either it's going to be some kind of frequency constraint, as Eddie Chen has suggested, or perhaps it's going to be the course of history is selected in a probabilistic way from some set of possibilities. But either way, you end up saying the course of history is determined all at once. So there's no sense in which I'm acting now and yet my future actions are still open. Even if they're probabilistic, they have, from this atemporal point of view, already been chosen.
I remember, oh gosh, I forgot who it was. Someone was saying it could be the Calvinists. Maybe it was a religion or maybe it was an actual philosopher, was saying that if you have trajectories in space-time, just because they exist and you can view it from a God's eye point of view, atemporally, it doesn't mean that those trajectories cause the movement. Those trajectories are the movement.
Yeah.
Sorry, are the trajectories. So an agent can still be causal. There's nothing about the trajectories causing. Like the laws don't cause. So can you please distinguish between the determination of an agent and causal origination of an agent?
Yeah. So because I think that causation is not fundamental in any case, I think that, understanding how the history comes about is not going to involve any kind of causal story. That's going to be some more general kind of modal constraint, perhaps, that selects the history. And causation is something that appears at a much higher level of description and probably is only going to be relevant in the kinds of regimes where you have agents taking actions. So I think it's perfectly possible to say, in some sort of fundamental sense, the history was already there and was selected in an all-at-once way, but nonetheless, the agent, is the cause of their action because causation is only suitable in that kind of regime of description anyway, and so it is still true insofar as there is such a thing as causation. It's still true that the agent is causing their actions.
Right. What do you disagree most with Carlo Rovelli on?
What I disagree most with? I think we still have an ongoing debate about whether it's sort of necessary to change relational quantum mechanics in the way that we suggested. We proposed a postulate that you can add to the theory, which makes it possible for observers to communicate with each other in an absolute sense and for their perspectives to become aligned in an absolute sense. Carlo, I think, is not convinced that's necessary. He thinks perhaps it's enough that there's it's relationally true that within my perspective, it seems as though I have access to your perspective, and he thinks that might be adequate. For me, I think that doesn't solve the kinds of epistemic worries I have about the role of social inquiry in science. So I think the absolute story is necessary, but this is an ongoing debate.
Now, many derivations in physics rely on integration by parts, and then they have this argument that, and the boundary terms are zero, and because of that, we get so-and-so. Are there times when these surface terms are ordinarily said to vanish, but because of your work on all at once, you believe that to be an unreasonable assumption?
Oh gosh, that's an interesting question. I actually have not thought about that. Seems very possible, but I would have to think more about the technical details before I could say one way or another.
Okay. What is self-location?
So self-location refers to scenarios in which you are uncertain about your location within the universe. So you might be uncertain where you are or when you are, or if you're in a multiverse, you might be uncertain about which universe within the multiverse you are currently located in. So it's those kinds of questions pertaining to a location within a universe.
And there's something between pure and superficial, if I'm not mistaken. What are those?
Yeah, so when we talk about self-locating uncertainty in philosophy or in physics, I think there are two importantly different classes of self-locating uncertainty that we should distinguish between. So what I call pure self-locating uncertainty refers to cases where you are uncertain about what location you are out of a possible class of locations which are all located within the same world. So, for example, Adam Elgar's case falls into that bracket. That's a case in which Dr. Evil, or a person who believes himself to be Dr. Evil, receives a credible message telling him that a subjectively identical duplicate has been made of Dr. Evil and placed somewhere. So in that case, he's now uncertain whether he is, in fact, the real Dr. Evil or the duplicate. But both of those people exist within one and the same world, so that is pure self-locating uncertainty. By contrast, superficially self-locating uncertainty refers to the case where you're uncertain about your location, but the possible locations you could be in belong to different possible worlds. So, for example, suppose you wake up and you haven't looked at the clock yet, so you don't know what time it is. You're uncertain about your location in time. But of course, in every possible world, there's exactly one time at which you actually wake up. And so the different possible times you could be located in belong to different possible worlds corresponding to those different possible times you could wake up. So that's, I think, an importantly different type of self-location.
Is this related to the Sleeping Beauty paradox?
Yes. So the Sleeping Beauty paradox, in fact, involves a mixture of pure and superficially self-locating uncertainty. So I think the correct way to analyze that is to appeal to your scientific theory to determine the superficially self-locating credences and then to assign the pure credences any way you want. So the outcome is that the correct solution is the double Hafer solution.
Okay. Well, it'd be useful for you to outline what the paradox is at this point, and then why you think the solution's the double half one.
Okay, yeah. So the Sleeping Beauty paradox refers to a scenario in which an experiment is being performed on you. You're going to be put to sleep, and then you'll be woken up either once or twice in the course of the experiment. We'll just decide which one it is based on the outcome of a coin flip. So we flip the coin, and if it lands heads, then you'll be woken once on Monday, and if it lands on tails, then you'll be woken twice on Monday and Tuesday. So the question is about what credences should you assign to the outcome of the coin toss? Should you assign and do the credences change if you're woken up and then told what day it is? So various different approaches have been taken to try to decide what the correct assignation of probabilities is. Most philosophers, I think, are of the view that when you learn something about what day it is, you ought to change your credences. My view is that because the coin flip is the coin flip issue is a superficially self-locating issue, whereas the issues about when you are located are pure. The outcome is that the further information shouldn't actually change any of your assignations of credences, because the right way to assign credences in these situations is always to assign the superficial self-location credences first, and then, having done that, arrange your pure credences as you would like. That means that the pure information isn't going to change the superficial information, and so the probability is always going to be half, regardless of waking up.
Now, was there something about when they say you get woken up twice, that after you get woken up once, you take something to forget that you woke up once?
Yes, you are not going to know that you've woken up at once or twice.
Now, what does any of this have to do with physical law?
Yeah. So self-location is important to physical law, particularly in the context of physical theories that deal with multiverses. So in particular, the cosmological multiverse and the many worlds interpretation of quantum mechanics has a multiverse. And in both of these multiverses, in order to make certain kinds of predictions, it's necessary that you assign some credences over locations within the multiverse. You have to assign probabilities to which universe you might be within this multiverse. And so all of those approaches to making predictions in a multiverse are kind of predicated on the assumption that there is, in fact, some objectively right or uniquely correct way to assign your self-locating credences over parts of the multiverse. And so, therefore, they are necessarily predicated on the claim that there are unique ways to assign pure self-locating credences. There's a right way to do it, and there's a wrong way to do it. So I think that's wrong. I think that for superficially self-locating credences, there are right ways to assign them because those credences can just be inherited from a scientific theory. But in the pure case, there is nothing whatsoever which could compel you or constrain you to assign your credences in any particular way. So any assignation of credences is fine, and therefore you're not going to be able to get meaningful predictions out of any theory which involves this kind of multiverse reasoning. So if I'm right about that, that's a serious problem, both for the cosmological multiverse and for the many worlds interpretation of quantum mechanics, because it seems to say that we can't make meaningful predictions in that context, and we therefore can't obtain any sensible evidence for scientific theories in that context, because there's nothing to sort of predict and then see if it comes true.
I'm sure you've spoken to Sean Carroll about this. So have you, and what has he said, or what do you think he would say?
I have not spoken to Sean Carroll about this. I know that Carroll has a view of the multiverse, which and of the Everettian multiverse in particular, which is based on the idea that certain constraints on self-locating credences can help tell you how to assign probabilities in the Everettian case. I do think this view says that approach is wrong. There are no rational constraints on self-locating credences in the Everettian scenario, and so any model which sort of takes that as a starting point, I think, cannot be right.
I believe in 1907, if I'm not mistaken, Einstein had his happiest thought about free fall and weightlessness.
Yeah.
Have you had a happiest thought?
And a happiest thought? I think one moment I'd pick out is there's a theorem in quantum foundations called the PBR theorem. The PBR theorem is about the reality of the quantum state. It attempts to prove that if in order to reproduce all of the predictions of quantum mechanics, it must be the case that the quantum state is a real objective thing which travels through time, conveying information from one time to another. And I think thinking about this theorem, one thing that struck me was that the whole theorem was predicated on the assumption of what I would call temporal locality. It's predicated on the assumption that if a measurement result depends on earlier preparation, there must be something which travels between them, carrying that information from one point to another. So that, I think, was the origin of most of my work on temporal non-locality, was the observation that there's this significant assumption being made in this theorem that is perhaps not being questioned in the way that it should be.
Do you have any thoughts about eternalism versus presentism? And can you please briefly define those terms?
Yeah, so presentism is a philosophical view which says that, in some sense, only the present is real, the past and the future are not currently real. Eternalism says that the whole of history is real at once. There's no sort of privileged present moment. It's all there. I am, as you might expect, given my views on all at once physics, I'm definitely more on the eternalist side. I think it's very hard to make presentism work in a way that is compatible with relativity, because relativity denies that there exists a global present, so it's kind of unclear what the present even is in that picture. And people have made attempts to sort of reformulate presentism in relativistic ways, but I think all of them feel a bit ad hoc and not very compelling to me. So certainly, in the context of what we know about physics now, eternalism seems to me much more viable.
Hi everyone, hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org. We talked about cubism, transactional, many worlds. What other interpretation of quantum mechanics have we not talked about that you feel fails significantly? And why does it fail?
The obvious ones are the sort of the primitive ontology approaches, so the Bohmian approach and the spontaneous collapse approach. I wouldn't say these approaches fail. What I'd say is that at present, we don't know how to reproduce the whole of quantum field theory in these kinds of approaches. And there are reasons to think we may never be able to do that, or that it's very difficult to do that in the context of this particular kind of view. So never say never, but right now I'm not sure the prospects for expanding those to cover all of quantum theory look very good. And, until we can show that that can be done, that's a sort of strong, compelling reason to be worried about those approaches.
So, what's on your mind these days, research-wise?
Research-wise, so I have been thinking about um, one thing I've been thinking about is a problem in relational quantum mechanics. So there's this worry. Relational quantum mechanics is committed to the view that all physical systems can, in some sense, count as observers. They can have quantum states defined relative to them. There's a worry brought up by Kassler Bruckner that it doesn't make sense to say something like a qubit is an observer because there's no way to get a well-defined basis in which a qubit could make an observation. So you just couldn't get a well-defined observed value out of an interaction involving a qubit. So I think he's right about that as an objection. I think the way to resolve this is to appreciate that the description of the world relative to a qubit is not going to be a full quantum Hilbert space. It's not going to be as complicated as that because a qubit just doesn't have the right enough physical resources to define that kind of relative description. So I've been trying to think about what would be a sensible way of formulating what the world does look like relative to a qubit, and thus of sort of understanding what the range of observations that something like a qubit could make might look like.
Do you then generalize a quantum system to a process matrix? Why don't you define what a process matrix is?
Great. Yeah. So process matrices are a tool developed within quantum foundations recently to study causal processes more general than those we would encounter in our ordinary space-time. So the idea here is that we'll start with a set of laboratories in which agents can do various actions, and we'll write down a description of the way in which these laboratories are related to each other. But we will not require that these laboratories have any sort of specific space-time location, and so we won't require that their relationships are constrained by the causal structure of ordinary space-time. The only constraint we'll put on them is that it has to be logically consistent, so they have to be related to each other in ways that won't produce logical contradictions. So what we can do then is end up with a description of a class of possible causal processes, which is much more general than what we would normally encounter in the world. And that is potentially going to give us an idea of what kinds of processes might perhaps be possible, for example, in certain regimes of quantum gravity where space-time in the ordinary sense breaks down or is perhaps not present.
The process matrix is another way of formulating or thinking about quantum mechanics, or what? Or thinking about the wave function? Or density matrices?
Yes. So, process matrices are quantum in nature, but they are much more general than ordinary quantum mechanics because, in ordinary quantum mechanics, we would tell a story in which you start with a state and just evolve forwards and produce everything in a well-defined temporal order. Process matrices retain aspects of the quantum formalism, but get rid of that evolution story. So we're not requiring that you can sort of tell a story about the temporal unfolding of how one laboratory leads to the next laboratory and so on. You allow much more general possibilities for how those laboratories could be related to each other.
Do you derive the Born rule, or do you have to assume it? Do you have to postulate it somehow?
In the process matrix formalism, it's not clear that the Born rule is even used. I think certainly understanding where the Born rule fits into that picture is an ongoing project that hasn't yet been fully resolved. But with that said, you can also formulate an equivalent of the process matrix formalism in purely classical physics. It's called the process function formalism. So that's perhaps conceptually a bit clearer. You don't have to worry about the Born rule and measurements, but you still have this idea that you can think about general causal processes without necessarily imposing a pre-existing space-time structure on them.
What's Humean supervenience, and what is its relation to asymmetric dependence?
Humean supervenience is the idea that the world is just a distribution of categorical properties over space-time. It's just, one thing and another thing and another thing. There's no sort of deeper structure or connections. And so everything else, including things like the laws of nature and the facts about causation, have to, in some sense, depend on or supervene on this distribution of actual facts. So, for example, the Humeans will say that the laws of nature don't make things be the way they are. All the laws are just sort of convenient descriptions of the way things happen to be. They're just the best systematization of whatever has actually happened.
In your model, what's at the ground? What do you take as your ontological commitments?
Yes. Well, I mean, the way I formulate that in the past is, we start from some space of possible courses of history, which might be an ensemble of, Humean mosaics composed of distributions of facts across space-time. And then we have constraints which determine which elements of that set are allowed by the laws of nature, and then some element of that set is going to be selected and made actual. So we have a sort of space of possibilities. The constraints narrow down the possibilities, and then one constraint is somehow selected. I think there's more work to be done here on understanding what the space of possibilities look like and how the space of possibilities is related to the constraints and to the properties that we see in our everyday lives. But that's the general picture, that you have possibilities narrowed down and then one is going to be selected.
So space-time would emerge from possibilities plus constraints?
Yeah, I think the story that we should tell about space-time here is certainly still a work in progress. In my previous work on the subject, I've just kind of taken space-time as given and imagined, let's select the constraints are just going to tell you how things are distributed across space-time. But certainly that, I think, can't be the right final answer because, modern physics and particularly quantum gravity tells us that space-time probably emerges from something more fundamental. So I think ultimately that the right story is going to be more complex than that. But exactly how to formulate that is not clear, partly because the quantum gravity itself is not fully formulated and there's still a lot of open questions to be resolved there.
What would it be that selects the specific dimensionality and signature, like 3+1?
Yes, that's a great question. Ultimately, I think at least some aspects of the way space-time have got to come from consistency constraints. So, for example, you can, if using the process matrix formalism, for example, you can see that there's going to be a need, if you want to have consistency, there's usually going to be a need for things to occur in some well-defined order. The well-defined order stops processes from looping back on themselves and producing contradictions. So I think from those kinds of consistency constraints, you can get already the idea that there's got to be some kind of something like a temporal dimension, which is different from the spatial dimensions. Mm-hmm. I also think you can get the idea that it needs to have a sort of a relativistic space-time structure from the observation that if you have superluminal signaling, for example, you can use that to create a loop which goes around and which could then also be used to create logical contradictions. So consistency is also going to give you something like the light cone structure of space-time.
Huh, interesting.
I don't know yet how to get exactly 3 dimensions out of that. It would be great if there were a way to get that as a consistency condition as well. I'm not sure what that would look like, but I think many aspects of space-time structure can be understood in that sort of basic way as consistency conditions.
Do you imagine that you'll be able to derive any of the fundamental constants from global laws? Or is there still, like, let's say alpha or G, mm-hmm. or is there still going to be some residual contingency leaving room for why these structures?
Yeah, that's a great question. So Eddie Chen has written before about this idea called strong determinism, which is the idea that maybe the laws of nature are so strong that they actually dictate the whole course of history uniquely, and there's only one possibility. That's in some ways an old idea. Leibniz hoped for something like that as well. Mm-hmm. It doesn't seem obvious to me how to get there from the laws that we currently know. And I'm skeptical that we could possibly know all of the constraints, even if there do exist a set of constraints that strong. But in principle, I think that it's certainly possible that there are constraint-based laws that we perhaps haven't arrived at yet and might be able to arrive at one day, which would give an explanation of some of those things.
Do you imagine there would be specific correlations between seemingly unrelated physical parameters?
Certainly, it's very, very possible. I mean, it's a bit hard to speculate because we don't have much of a sense of what that would look like. But certainly, if we could give explanations for or relationships between the values of things, that would be a very, I think, compelling piece of evidence that this right way of thinking is right. So it's certainly something to look for.
Are you more interested in the philosophy of physics specifically, or more broadly into the philosophy of science? What about metaphysics? What about ethics?
Yes, I do focus largely on the philosophy of physics because, my training is in physics. But I think many of the questions we are talking about in the philosophy of physics have really interesting implications for more general questions in the philosophy of science. So these questions about the nature of lawhood, for example. And I think once you move to an all-at-once style account of laws, that's going to have implications for a lot of other traditional philosophical questions about things like causation, explanation, determinism, and so on, free will. So although, my focus comes from physics, a lot of that expands more generally into philosophy of science and also metaphysics, because these questions about lawhood, causation, explanation do also link to metaphysics. Ethics, I'm very interested in ethics. I've never worked on it professionally, though. So.
Cool. Do you have any advice for young upcoming researchers in the field of physics and philosophy?
I think my biggest piece of advice would be to work on the things that you love and are interested in. I think there can be a pressure to work on something that is currently one of the hot topics, or that is getting lots of attention in the field at the time. But ultimately, I think what's most rewarding and what will be successful in the long run is for you to pursue the things that you care about and do the work that you're interested in. And, it might take a little bit longer to get attention, but I think it's better to ultimately establish that program of things that you really care about, rather than feeling you have to do research on a certain topic because it's popular.
What's some topic that's underappreciated that you think should be more appreciated? So I'll give you an example of something that's a hot topic right now:
Yes.
Black holes.
Yes.
And supermassive black holes and time travel or time dilation, etc.
Yeah.
And those are said ad nauseum in these popular science circles. So what's something else that you think people should be paying more attention to?
I'm on a bit of a crusade to get people to pay more attention to the epistemology of the measurement problem. I think the measurement, when we talk about the measurement problem, it often gets framed in terms of ontology, in terms of we need to know what is really there and what is really happening. Whereas for me, I think the measurement problem is really important precisely because it ties to questions about how could we possibly know the things we are supposed to know? How can we make sense of the empirical confirmation associated with quantum mechanics? And I think that a number of very popular interpretations of quantum mechanics have really big problems answering those kinds of questions. So particularly the many worlds interpretation and the observer relative interpretations have really bad epistemic problems, and I think do not do a good job of answering these epistemic issues. So I really like to see our discussions of the measurement problem focus more on these questions of you've got to make the epistemology coherent and consistent within itself. And I think that's a good way of kind of narrowing down the possibilities and understanding what a viable solution looks like.
Can you repeat these epistemological questions that you think people or physicists or foundational physicists should be thinking about?
Yeah, well, I mean, the fundamental question is that when we're thinking about how to interpret quantum mechanics, it is, I think, essential that our interpretation tells a consistent story about how we could have come to know about the theory. So, for example, I think the many worlds interpretation has a real problem with this because the many worlds interpretation has difficulty giving meaning to assignations of probability to measurement outcomes. And in particular, it seems hard in the many worlds context to justify the claim that you should expect to see high probability outcomes. But if you can't expect to see high probability outcomes, then you can't use the outcomes you have observed as evidence for the theory, because you have no idea whether the outcome is one that's assigned a high or a low probability by the theory. So you can't connect it back up to the structure of the theory you're trying to find out about. So I think that's a very serious epistemic problem. I think similar problems arise in the observer-relative approaches. And I think those kinds of problems should be much more to the forefront when we have these discussions about how to interpret quantum mechanics.
What's a lesson, Emily, that you wish you had learned earlier, that if you could tell your younger self, it would be beneficial?
Oh, gosh. um, I think probably, as many people would tell their younger selves, I would counsel patience. That it, it takes this kind of thing. Research definitely takes time and work, and you will fail many times, and many things will not go anywhere. And I think you have to be persistent and hang on and have faith that in the long run, you're going to come to interesting results, and people will eventually come to be interested in what you're doing. And it does come eventually. It takes time. It doesn't happen immediately.
So was there a time, maybe a year, 3 years, 4 years, where people weren't interested in your work and that frustrated you or made you downcast?
I think for some time I was worried that the kind of work I was doing was not going to ever be sort of mainstream enough for me to be able to make a career in the field. I actually left academia for a few years and worked outside of it because I was pessimistic about whether I could do the kind of work I wanted to do and be in the field. But eventually some of the things I was doing, I did get positive feedback on, and that I think was enough to encourage me to come back and keep working on this stuff. And I don't regret that. I think that was the right decision. But yeah, I think looking back, perhaps if I'd understood the need for patience, that could have been avoided.
Tell me about that. So you left academia for a while, and then were you still publishing while you were outside?
Yeah, I did. In my PhD, I mostly published on pure physics topics. After finishing, I left academia, but continued to think about particularly more philosophical topics and to publish and to write on those things. And eventually, I think, came to the realization that clearly this is what I should be doing professionally. And so then sort of wanted to switch from the more physics side into the more philosophy side.
How did you get back in?
Yeah, it wasn't straightforward, especially because I was looking for philosophy positions and had physics qualifications. But the people at the University of Western Ontario were very helpful and encouraging, and found a way to bring me there and allow me to do a postdoc there. And that was a very, very productive time, really fantastic. And so that was my route back into the field.
Well, it's fantastic speaking with you. Thank you so much for spending your time with me.
Yeah, this was really fun. Thank you. Cheers.
I've received several messages, emails, and comments from professors saying that they recommend theories of everything to their students, and that's fantastic. If you're a professor or lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, Toll listeners also gain from replaying. So how about instead you re-listen? on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal. There's also crypto. There's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.